Hello APC Mechanics students, today we'll solve the past paper FRQ 2019 Set 2 Exercise 2. A toy rocket of mass 0.5 kg starts from rest, which means that the initial speed is 0 on the ground and is launched upward, experiencing a vertical net force. The rocket's upward acceleration A for the first 6 seconds is given by the equation A is k minus lt square, where k is 9 meter per second square and l is 0.25 meter per second to the power 4 and t is the time in seconds. Now notice that k and l, their units are given in such a way for this equation to agree via dimensional analysis. At t is 6 seconds, the fuel is exhausted and the rocket is under the influence of gravity alone. Assume a resistance and the rocket's change in mass are negligible. Basically here we have a problem consisting of two phases. In the first phase, which is from 0 to 6 seconds, the rocket is under the influence of a net force that yields to an acceleration given by k minus lt square. After the 6 seconds in phase 2, the rocket is under a free fall motion, which means that the acceleration is due to gravity only. Now in part A, we need to calculate the magnitude of the net impulse exerted on the rocket from 0 to 6 seconds. We know that the impulse given by J is given by the integral from f dt. Now this is a bounded integral because we're doing that from 0 to 6 seconds, so 0 seconds to 6 seconds. Now the force is given by the mass multiplied by the acceleration, ma dt. Now we're assuming that the change in the mass is negligible, so the mass is a constant. Now A can be replaced by the given acceleration given by k minus lt square. Now here let's expand. That would be mk minus mlt square. Now we're ready to integrate. This is a constant term, then we're gonna have a linear term, and this is quadratic, would have a cubic. And we should compute the following expression between the instant 0 and 6. Now the mass is given by 0.5, k is given by 9, and for the first instant, so remember that we're computing this at 6 minus this again computed at 0. Now L is 0.25, the final time is 6. So all of this expression minus again this expression computed at 0. If you replace time by 0, that would be 0, and if you replace time again by 0, that would be 0. Now plugging that expression on the calculator, we're gonna have a value of 18. Now the unit of the impulse refers to f multiplied by time, which is in Newton seconds. Then the impulse for this duration is given by 18 in Newton second. Now in part B, we need to calculate the speed of the rocket at a specific instant given by 6 seconds. Now the first glance, you cannot use any of the kinematics equation related to uniform motion, simply because for this phase the acceleration is not constant and it's governed by the following equality or equation of motion. For this reason, we need to approach the problem in a different way using calculus, and we know that the speed or the velocity is related to the acceleration via an integral. Now let me set this integral as a free integral or indefinite integral, and we have that the initial speed is 0, so we can determine the constant. After that, we're gonna compute the velocity at t is equal to 6 seconds, and then we can deduce the speed, because we know that at some point velocity and speed, they aren't the same. Now that would be the integral of k minus lt square multiplied by dt, and that would be, so we have done this integral before without or with the mass, and now here we have a constant. Now because this is a polynomial function, then this would represent the initial speed, and we know that because the rocket started from rest, then the initial speed was 0. However, we can ignore this fact and we replace the value for v. Now, so let me here state again that the speed is given by kt, or the velocity. Now why this is the velocity? Because we are integrating acceleration. Now if we replace t by 0, the initial velocity is 0, that would be 0, and that would be 0 plus c, which makes the constant c to be 0. Then now we know that the velocity is given by kt minus lt cubed divided by 3, and we need to calculate the velocity at a specific instant given by 6 seconds, which means the value of k, which is constant, is given by 9 multiplied by 6 minus 0.25 divided by 3 multiplied by the time, which is 6 to the power of 3, and that would give us 36 meters per second. Because the velocity is positive, which means that the speed also, then the speed at t is 6 seconds, is given by 36 meters per second. Then this is it for part B. Now in idea C, part C, idea 1, we need to calculate the kinetic energy of the rocket at t is equal to 6 seconds. We know that the kinetic energy is given by the quadratic term half mv square. The mass is given by 0.5, and at this particular instant the speed is given by 6. Plugging that on the calculator, we're gonna have a value of 324. Now kinetic energy is in joules, which means that the kinetic energy at this specific instant is given by 324 joules. Now in C idea 2, we need to calculate the change in the gravitational potential energy of the rocket Earth system from 0 to 6 seconds. So remember that the rocket is going upward, which means the work done by gravity is negative. However, the change in the gravitational potential energy is positive. Now the change in the gravitational potential energy is given by gravitational energy final minus gravitational energy initial. And here let me state the following. That we're gonna take the PE level to be the ground, which makes this to be 0 because initially we're at the ground, and the final gravitational potential energy with respect to the ground is given by mgh. Now we know the mass, which is 0.5, we know g. Now generally we take g to be 10, but since this is a free response problem, we're gonna take it to be 9.81. And in order to find the height from 0 to 6 seconds, also here let me make the following comment. We cannot make use any of the kinematic equations related to uniform varied motion. We need to use calculus. Then let's determine the vertical position derived from the velocity. The vertical position is given by the integral of v dt. So which is basically the integral from, so v is given by kt minus lt cube over 3. Now here I'm setting this integral to be a free integral. Then I'm gonna determine the value of c, and we're gonna substitute for y equals to 0, and that would be kt squared divided by 2 minus lt cube divided by 4, and already we have 3 here, plus the constant c, which makes it kt squared divided by 2, which makes it now lt cube divided by 12 plus the constant c. Then the vertical position is given by kt squared divided by 2 minus LT cubed divided by 12 plus C. Now if we're starting from the origin at T is equal to 0, this means that the constant C is 0. Now we know that the vertical position is given by K T squared divided by 2 minus LT cubed divided by 12. Now if we need to determine the vertical position, which is H, corresponding for T is equal to 6 seconds, that would be K is given by 9 divided by 2, 6 to the power of 2, minus 0.25 divided by 12, and that would be 6 to the power of 3. Plugging that on the calculator, we're gonna have a value of 135 meters. Now we're ready to determine the gravitational potential energy, which is the mass 0.5 multiplied by G, which is 9.81, multiplied by H, which is given by 135. Plugging that on the calculator, we're gonna have a value of 662 joules. Then the change in the gravitational potential energy is given by 662 joules. Now in part D, we need to calculate the maximum height reached by the rocket relative to its launching point. Maximum height corresponds when the speed is 0. Now remember, here we have two phases. So let's assume this is the ground, and here would be phase 1, and here would be phase 2. So from phase 1 to phase 2, we started here initially from rest. Here we have gained a speed of a velocity given by 36 meters per second upward. Now for phase 2, the acceleration or the rocket is only under the influence of gravity. So we need to deal with the problem in phase 2 as a free fall problem, and we need to determine the height traveled by the rocket in phase 2, governed by the acceleration, which is given only by G. Now in phase 1, the distance traveled is given by 135 meters. So in order to do so, let me state after T equals 6 seconds, the rocket is launched upward by velocity of 36 meters per second under a free fall motion. Now we know that the height in this case traveled would be given by v squared divided by 2g, but we're not allowed to use any shortcuts because this is a free response problem. Then I will derive this expression using energetic approach. For this reason, I will say I'm gonna reset my PE level, take the PE level to be the position at T is given by 6 seconds. And why we're allowed to use conservation of energy? Simply because assume air resistance is negligible, so we don't have any frictional forces. And I will say apply conservation of energy. Which means energy final would be equal to energy initial. Now the final energy is given by kinetic energy final plus gravitational potential energy final. And initially we have, so here the initial point is at t is equal to 6 seconds. The final point after it reaches a maximum height with the vanishing speed, now that would be kinetic energy initial plus gravitational potential energy initial. Since we're taking the P level to be at t is equal to 6 seconds, that would be 0, and my final speed is 0 because we're determining the maximum height, which means we're using mass for small m. mgh is given by half mv square, and we can simplify with m, which means that h is given by v squared divided by 2g. Now the speed at 6 seconds, which is my initial instant, is 6. That would be 36. That would be 36 to the power of 2 divided by 2 multiplied by 9.81. Plugging that on the calculator, we're gonna have a height given by 66 meters. Then 66 meters would be added to 135, which represents the total height during the two phases. Then let me say, then the maximum height is given by 135 plus 66, which corresponds for 201 meters. And now for the final part E, on the axis below, assuming the upward direction to be positive, sketch a graph of the velocity v of the rocket as function of time t from the time the rocket is launched to the time it returns to the ground. T top represents the time the rocket reaches its maximum height. Explicitly label the maxima with the numerical values, all algebraic expressions as appropriate. We know that the maximum speed reached by the rocket is given by 36 meters per second. And at the top of the flight, the speed would be given by 0. Now, for the first phase, the velocity is given by kt minus lt cube over 3. Now basically what's gonna happen is that for the phase 1, let's assume this is phase 1, the rocket will start from an initial speed, reaching a speed given by 36 meters per second. After that, which corresponds to the phase 2, the rocket will be only under the influence of gravity, and because A is constant, which means that V would be linear, and in order to connect this point with the vanishing velocity, the only way that would happen via a straight line. And now what's remaining is that how we should connect the initial point with the final point, and this depends on the concavity of the curve. The concavity can be determined from the double derivative of V, because we're plotting V. The first derivative is given by k minus lt square, and the double derivative is given by minus the double of lt. And as you can notice that here, that this is negative, which means that the curve would be concave downward, and we'll connect the initial point to the final point with a downward concavity like that. Alright, then that's it for me in this video, guys. See you soon in a new one.